the aircraft.
Yeah.
You remember that?
You mean the part? I mean, I was going to explain with the budget analysis why we see it in the simulation, but you mean the mystery? Are you asking about why they were able to find it even though it was between flight levels?
Yeah, yeah.
Oh, yeah.
I checked the original paper and found that they did observe the warm core. They did observe the warm core. Maybe the flight level might be not exactly the 650 hectopascal.
But this isn't from. This is still from the aircraft data, right? There's no drop sounds here. These aren't real sounding.
Yeah,
right?
so they should fly maybe the 220 hectopascal.
Yeah.
The flight level might be not exactly 650 hectopascal. It pat out and hit the wall. Because they use the only 5 flight level data, and they have this peak. Just below the 600, between the 600 hectopascal and the 650 hectopascal.
Yeah.
So it seems to they fly the.
You think they flew at the level of the peak?
Yeah. Because the hurricane was very, very small tropical cyclone. And when they try to fly straight, they suddenly happen to meet very low pressure in the eye. It might be the flight level might be recorded 300 for example 320 hectopascal in the eye. Doesn't this make sense?
But
They can. Is this peak? But was this peak was reserved?
I'm not sure. I think I would need to read more carefully. I don't know. I mean, so you're saying they deviated the pressure by the small amount as they flew into the eye, or?
Suddenly drop the pressure in the eye, and this indicates the pressure indicate they fly not exactly 650 pascal.
Yeah, but at any given flight, you're flying like through the eye. They're flying at a given level, and so they don't have observations below or above the flight. So it still would seem hard to tell if you're actually the maximum.
I mean they fly through the not exactly the 650 50 millibar. The flight level was pattern.
Yeah. Yeah. I guess what I'm saying is, so if it was perturbed and they were at say 650, then they no longer know what was at 600. So you still don't know if the temperature is higher or lower.
Somebody very frequent in English can help me. Fluent in English can help me.
I mean, I think I understand. Like you're saying that they were actually flying here.
Here.
Yeah.
In the pressure level.
Because there's no GPS measurement of the altitude, so they don't know the real altitude, and they use the pressure gauge for measure the altitude. So the real altitude should change.
Yeah. Okay, that's possible. I don't unless. At some point they had a radar altimeter to know their true altitude. I don't know if they had that for this flight or not. Do you know?
In this era, I think there's no radar altimeter.
Okay.
They have only pressure and
Radio.
Okay, so you think that where they actually sampled was the maximum, but when they plot it versus the pressure that they're reconstructing, that shifts the height. That could be, but I think this upper level maximum is so far away from where they were flying here that it's hard to explain it by that. And the other flight, the Hurricane Cleo flight, they plot the maximum well above where they have any flight. So I think there's still maybe some influence from the interpolation and the extrapolation procedure where they're making assumptions about lapse rates.
And in this era, the interpolation is not purely the objective.
Yeah.
Sometimes subjective.
Yeah. Yeah, I remember there's like a description in the paper about like some 4 or 5 steps of the assumptions they're making to try to reconstruct the sounding, and I think they're assuming they're trying to use hydrostatic balance to infer some aspects of it. But yeah, you may be right that can also, perhaps the mid-level one they're actually flying through the maximum and then it's just plotted differently. So that could be.
Yeah, it's our guess. Guess from Canada-san.
Yeah.
She sent an email to us about this point in the midnight.
I just take the original paper.
I'll reread the paper at some point and I'll see what I think.
Okay. Okay, so we'd like to have Dr. Dan's seminar continuously from yesterday, and today's topic is tropical cyclone warm core, and next we'd like to have a topic about understanding extreme updrafts and wind gust using drop zone observation and radiated simulations. So from middle of the part 2, you would like to start. So, okay, so again, please welcome to Dr. Daniel Stan.
So, I'll continue with the warm core topic that I was started with yesterday, and maybe we can take a break at the end of this lecture before the next one, and we'll see how the timing goes. But we have 3 until 12 today. Is that?
Until 12.
Yes. Okay. Let's go just backwards a little bit. And so yesterday we were talking about how in numerical simulations, I found, and some other studies have since found, that you can often be a mid-level maximum in the temperature perturbation. And sometimes there's 2 maxima with an upper-level maximum that, in my simulations at least, are usually weaker than the mid-level maximum, but some other simulations it's the opposite. And that this is consistent with the early observations from Hurricane Inez, and also consistent with the mid-level maximum from the Halverson et al. Study. And so in the observations, it's hard to determine why we get the temperature structure that we think we observed, but in the simulation we can do a more in-depth analysis to try to understand what's the cause of the structure. And so that leads to the start of the lecture today, which is why is the warm core maximized at mid-levels in simulations. And so to try to answer this, I performed a potential temperature budget on the same simulation that I've been talking about, this idealized simulation. And this is shown in this 2013 paper. And there's also the simulation I'm showing here. It has no wind shear, but I also did simulations with wind shear, and those are presented in the second paper from 2013. And I'll just say that the results are largely similar for those simulations. So I'm going to try to answer a couple questions. Where is the largest warming found? We can guess where that is based on the warm core analysis that I showed you. And then what terms are important and what terms may be dominant in the physical processes that warm the eye. And then Finally, does the answer to these questions depend on the intensity of the storm? Does the processes that are warming the storm, do they vary with the intensity of the storm through the life cycle of the storm? So this is, these are the terms that I've examined in this potential temperature theta budget. So I'm showing the changes in theta, but largely it's going to be similar to the changes in temperature as well. There's just a difference in the magnitude and a little bit difference in the structure because of the pressure dependence. But theta is a much easier quantity to examine in a budget than temperature. So I split things into four main terms. One is the total advection of potential temperature, and so that's the sum of horizontal and vertical advection. And then heat is diabatic heating. So this would be the condensational heating as well. Basically, the contribution from the microphysics parameterization scheme. So that's condensation and freezing, evaporative cooling. It could include radiation, but in this simulation, I don't have any radiation turned on, so that is not in the budget. Then PBL, that is the tendency on potential temperature from the planetary boundary layer parameterization. In this case, that's the YSU parameterization scheme. So also note that the PBL tendency, it's not only in the boundary layer itself. The PBL scheme will provide parameterized vertical mixing throughout the depth of the atmosphere as well, but only the vertical turbulent diffusion. So the horizontal diffusion is handled separately in the WRF model. And so this HDiff term, that's the tendency from subgrid horizontal diffusion, as well as there's a Rayleigh damping layer in the upper troposphere or lower stratosphere to absorb gravity waves. So that would be above 16 kilometers.
Excuse me.
Yes?
Is the vertical diffusion included in PBL term?
Yes, the vertical diffusion is in the PBL term.
About the free atmosphere?
Both in the boundary layer and in the free atmosphere. It's small in the free atmosphere, but it's included within that. It's that how it handles the parameterization is different within the free atmosphere and within the boundary layer, but they're both part of the PBL scheme. What was
This one. I don't know how to delete it. This stuff. I tried to delete it, but I don't know how
remove
to
it.
do this.
Oh, that's interesting. Oh well.
So,
Just ignore whatever's down there. Yeah. So here's the four basic terms, but then we can decompose the temperature advection into four different terms. The mean vertical advection, W bar d theta bar dz, and then the mean radial advection of potential temperature. So this is just the azimuthal mean radial velocity and the azimuthal mean potential temperature gradient. And then you also get these eddy terms. So the convergence of the eddy fluxes of potential temperature. So eddy radial advection and eddy vertical advection. And it turns out, I'll show that the eddy radial advection is somewhat surprisingly important in warming the eye for some of the time. And I'm just showing you this plot again to tell you when and where we're going to examine the potential temperature budget. So I'm going to show you a budget that's a function of radius and height. This is showing the time height plot of the perturbation temperature at the center of the eye. So we're going to examine the warming of the eye, and I'm going to show you a budget for 3 consecutive 12-hour periods from 24 to 36 hours, 36 to 48 hours, and 48 hours to 60 hours. And that encompasses much of the period of rapid intensification of the storm. If you recall from yesterday, actually I'll just go back just to remind you with the time series of the intensity. So From 24 to 60 hours, the storm rapidly intensifies from a tropical storm to a Category 3 or 4 hurricane. And this is the time when the rapid warming happens, especially at mid-levels. And so yeah, you can see the references for the intensity categories, how it's changing during this period. So we're going to examine what leads to the formation of this mid-level maximum and how the temperature changes in time. So this is there's a lot going on here, but so these are the budget terms for that first period from 24 to 36 hours, the start of rapid intensification. And so the next this and then following two slides are going to be the same terms, same figure panels, but for the different times. So on the upper left is the 12-hour change in potential temperature in degrees Celsius or Kelvin over this period, and the color bar is on the right here. So dark red would be a 6-degree change over a 12-hour period. And then all the budget terms are also Kelvin for 12 hours. The magenta line contour on each plot is the azimuthal mean updraft of 10 centimeters per second. So that's the eyewall. So everything inside to the left of that magenta curve, that's the eye. And then each of these plots is showing the inner 50 kilometers. So R equals 0 is here, so up to 50 kilometers. So the eyewall's out in about 30 kilometers radius. And then this is showing the lowest 16 kilometers of domain. So
Excuse me.
Yes.
They all use the same, color bar,
yes,
same order.
yeah, all use the same
Same
color
color.
bar,
Okay.
which is for the tendency terms, it's the average tendency over that 12-hour period in Kelvin for 12 hours, and then the upper left, that's the actual change in the potential temperature in the model. So in theory, all the budget terms, so let me just, so the top center is the the tendency from total advection, so horizontal and vertical advection, all the advective tendencies. On the upper right is diabatic heating. In the middle, on the left, is the tendency from the PBL scheme, and the middle is the tendency from the horizontal diffusion. So in theory, if we have an accurate budget, these four terms should agree exactly with the actual change in potential temperature. And I don't have the plots here for the error analysis, but if you look in the paper, overall, the error is acceptably small. The budget closes relatively well. And so here, the change in potential temperature over this 12-hour period, we have two warming centers, actually, maybe three. And so we have, in this case, concentrated warming at low levels at 2 kilometers, and then this mid-level maximum about 7 kilometers. And if you recall, that's about where the warm core is really forming, is in this mid-level region. And then there's some tendency to have another maximum up at about 13 kilometers, which is near where eventually you get a secondary upper level maximum in the perturbation temperature. So this is showing us how the temperature and the potential temperature field are changing in time, and that will lead to the evolution of the perturbation temperature structure. So we can immediately see that the total advection tendency is very similar to the actual change in the potential temperature. And so what that means is that advective tendencies are dominant in warming the eye at this time. This white region here, those are less than -6 per Kelvin for 12 hours, so that's That's tendency in the eyewall is from advection is negative because of the adiabatic cooling from the vertical motion in the eyewall. So if you compare diabatic heating to the total advection, in the eyewall, they're opposite. So basically, you have huge diabatic heating that's much greater than the scale here. It might be 100 Kelvin for 12 hours, but it's nearly entirely offset by the mean vertical advection. So you don't get much warming in the eyewall because your condensational heating is canceled out largely by the adiabatic cooling. So in the eye, we do not have much diabatic heating because we're largely cloud-free and no convection, and so advection is dominant. You can see the maxima. We have two maxima in the total change, and they align well with the advective tendencies. The PBL tendency at this time is small in the free atmosphere. It's only large very near the surface. Horizontal diffusion at this time is very small, and that's because the storm is weak. The gradients are not that large. And mean vertical advection in the eye is large. However, it's interesting to note that the mean vertical advection in the eye at this time does not agree that well with the the actual change in potential temperature, or the total advection, which is the sum of the horizontal and the vertical advection. So we actually have, at mid-levels, at about 7 kilometers, we have a negative tendency for mean vertical advection. And what that means is that there's actually ascent, there's rising motion in the mid-level eye at this time. So we're warming the eye even though you're actually getting adiabatic cooling. So this is interesting because what it shows that you don't always just have descent warming the eye. You can have a warming of the eye even in the presence of anomalous upward motion. The low-level maximum in the tendency is well explained by the mean vertical advection. So this large warming of the low-level eye is due to subsidence at this time. And then this upper-level maximum is also due to subsidence. On the lower left here, the mean radial advection. So this is the inflow and outflow rearranging the potential temperature field. In the eyewall, it's moderately large because we have, and positive because there's outflow in most of the eyewall, and because the temperature structure of the eye, it's warmest towards the center, so you have a negative radial gradient, so outflow is going to bring warmer air. So the eyewall there's a warming tendency from the radial advection. In the eye, there's very little tendency for mean radial advection, and that makes sense because the gradients in the eye are near the center of the eye are small, and more importantly, the radial flow is very weak in the eye in a mean sense.
Dan, I'm sorry, I'm a little bit confused.
Okay.
Just let me clarify. This is our potential temperature, not temperature. So, how our adiabatic cooling can appear in the vertical advection? So I think it's not so simple story.
In the vertical advection, sorry, you're right, but it is a cooling tendency. It's because the temperature, potential temperature is increasing with height. So if you have ascent,
So vertical motion
yes,
every time,
yeah,
so causes the cooling.
yeah, vertical motion causes a decrease in the potential temperature because you're bringing lower theta from below.
Right.
And
That
yeah,
makes
sorry,
sense.
when you transform it to temperature space, you're getting even larger actual cooling because of the adiabatic.
I think in this case, adiabatic cooling cannot be seen, right?
Yeah, you're right. I should say for potential temperature,
Like
it's not cooling from expansion.
Original profile of potential temperature.
Yeah.
You can see this result.
Yes, yes. So because the atmosphere is statically stable, potential temperature is increasing with height. So anytime that you have a negative tendency from vertical advection of potential temperature, it means there must be upward vertical motion there.
So in that sense, the mean vertical advection near the center location, it means that, original profile affects the result, or like, vertical profile near the eye region can be related to the cooling in the eye region.
That the initial profile?
Maybe not initial profile, it should not be.
I think at this time it's probably not the. I don't think that it's sensitive to the initial profile.
I think so. Potential temperature, profile. You can see that not that this is just a change, but if you plot the potential temperature profile, maybe this is a location. Maybe the cooling and warming location is corresponding to the upward motion and downward motion, right?
Yes, that's the point I'm trying to make, is that I don't have a plot of potential temperature itself. I have static stability plots later, but potential temperature is just it's increasing with height. So wherever this is negative, this corresponds to upward motion, and where it's positive, it corresponds to downward motion.
So secondary saturation plot may help the understanding of this plot, right?
Yes, and that's a little bit later.
Okay.
Well, maybe just to clarify it, I'll just skip ahead for a moment to show you the vertical motion. So this shows the average vertical motion in the eye for these 12-hour periods, and so this is the one I was just showing you the budget for. And so this region of ascent, this is each contour is here is I believe 2 centimeters per second. So this is 4 centimeters per second. So weak, but over time, slowly rising motion, and that's going to, from that vertical advection alone, on its own, that's going to have a cooling tendency on the potential temperature because it's bringing up lower theta.
Right.
And on the actual temperature, it's also going to be cooling because of adiabatic expansion.
Thank you.
And so this is somewhat an anomalous picture to what we think. We tend to think of the eye as just being a region of mostly uniform descending motion. But in this case, even though this is a period of rapid warming throughout the eye and a period of rapid intensification, you can have this several kilometer deep layer where you're actually having upward motion in the eye. And it's not convection, it's just the mean forced circulation is upward at this time.
So this cloud, updraft, cause a stratiform cloud in the middle troposphere.
I don't know. I didn't examine the cloud field there. It might, but I think it probably doesn't because it's extremely dry there already. Mm-hmm. So my guess is there is not a cloud there. Mm-hmm. And this is again, this is not. This is an average over 12 hours. So it's. If you looked at an instantaneous snapshot, you would not be able to see this at all. You would see like kind of chaotic gravity waves, upward and downward motions of maybe a half meter per second to a meter per second, and it's only when you average high frequency data over a long period of time that you can really capture the mean structure here.
So I think it may be related to the secondary radial motion going to the eyewall region, is it right?
It's the inflow
from eye to the eyewall region.
Eyewall.
It might be related to this. It seems to me, you can see 24 to 36. You can see the downward motion in upper level and upward motion in between. So you can see the radial motion going from eye region to the eyewall region. So it might be related to some entrainment. Might be.
It could be.
From eye to eyewall region, this interaction between the middle level might be important rather than the low
So
level.
in this sense, there should be a detrainment from eyewall in the about 4 kilometer below the 5
I've seen
kilometers.
several such kind of features.
It is true in your simulation.
So in my simulation.
So